Hello developers, let's start developing. Today on the program is the 15th task of the 2022 Advent Code. And I've taken a look at the task. I'm not going to pretend that I'm reading this for the first time. That was fun for the first few, but now it does take some thinking. Maybe it's coming up with a strategy. I'm seeing the second part for the first time on this video, but the first part I've seen. So we have some kind of an input that will be quite easy to parse using regex, and I will explain while I'm parsing it what does it mean. We have some sensors that we're putting on a rectilinear grid, something like this. Again, we have our x and y coordinates, and actually x and y coordinates, and by now you learned that I like to do them the wrong way around. Programming wise, so we have the y coordinates come first and then the x coordinates in my matrices, and we have some two kinds of things. We have sensors that we deployed and we know the exact locations, and we have some beacons, and each sensor detects its closest beacon. So this one will detect that this is the closest one, this one will detect that this is the closest one, and I think that a lot of them will have the same. For example, these two beacons, these two sensors saying the same beacon is the closest, and that's great. How they determine the distance? Well, they use the Manhattan distance. That's the so-called taxi cab geometry, which is not quadratic as usually with Euclid, but it's linear. So to say, if we want, it's also called, it has the reason that it's called Manhattan distance because this could literally be a map of Manhattan. So it doesn't matter, you cannot follow the green line since it doesn't go that way. You cannot walk through buildings. And the yellow, the blue, and the red are exactly the same length. So it doesn't matter how, it's a sum of how much you need to go up and left. Anyway, it's linear, so it's relatively easy to calculate. So we have that, and we need to find out there is a beacon that is having some distress. So we need to find out where that beacon isn't. For example, we have this sensor and this beacon, and we have a circle. In Manhattan distance, this is a circle. This is a set of all points that are distant, equidistant to a given center, and here S is the center. So all of these points have the maximum distance or less than it. So a circle is basically what's inside of a line, the line of the circle. So we can know for a fact that the distress beacon cannot be in any of those fields, because if the distress beacon was in one of those fields, then this beacon won't be the closest one. So we can eliminate all of those as basically not one of the conditions. Now, of course, the first question you have, what if there's a beacon right here? Why isn't that the closest one? When the task solved that problem by saying that's not gonna happen. Yeah, there is never a time where two beacons are the same distance to a sensor. Okay, so we have sensor. Now, regarding the input, we will need to create a list of sensors and a list of beacons and a list of, and each sensor will have its closest beacon as a property. So this is relatively straightforward. We have x equals a bunch of numbers, more than one potentially. And let's take the big input as well. Do we have negative numbers? Yeah, we will need to paste to take care of this input as well. So for now, let's imagine that it's just positives, and then we have a comma and y equals, we're gonna need that, and then that is some numbers, and that then colon closest beacon is at, and then is something that is very similar to this, and then it basically ends. And yeah, we didn't match the first one because here we have a maybe minus. And we extracted the correct value. Okay, here we have a bit bigger numbers. And we matched everything except here because we have a negative y. Yeah, negative. Yep. So one thing that we need to notice is that, well, while our example has relatively low numbers, few numbers, actually the size of the input is about the same, so that doesn't, it's not a factor, but the numbers here are 3, 25, 2, 8, yeah, basically number one numbers. And here we have 2.5 million, some million, something. So my first initial guess is that this might be, we might have something that is efficient for small numbers if we do an exhaustive search, but not so efficient for large numbers. Nonetheless, let's try to solve it for this input here. And we have our regex, so the sensors are always positive, and the beacon can be negative as well. That is the thing we want. So we're gonna process our input. We're gonna have this line first, lines, and now we're just gonna map the lines to something. We're not just gonna trim it, we're gonna run some code, we're gonna do a line dot match slash slash. This is the regex that we want to do. It's a terribly specific regex, and we're gonna set this to match. And now, yeah, if we don't have a match, then we're gonna blow up because we should have a match. We can just say return sensor has an X and a Y, and a beacon has an X. And this runs mapping, and this is the actual input, and we're just gonna return them. So that means what is our input? We can have an interface point that is X number, Y number. Okay, that's cool. And then we have an interface sensor, which has a location, which is a point, and which has a beacon, which is a point. And we're not going to be using string arrays. We're going to be using not beacon, sensor. Sensor array, actually. And now we will have to put that in everywhere because search and replace, we did the search and replace from single sensor, it's a list, a collection. We're calling this location right now. So let's just log the input and see if it's here. Cannot read properties of null. Oh, it cannot read your input if you're not do not don't put your input. So we're gonna put our input here, save it, and yeah, I managed to have this be sensitive to input changes as well. And we have our locations and we have our closest beacons. So first of all, first thing that I'm gonna want to do in the processing is basically to have a beacon set. Will this work? Not really. We need to extract the distinct beacons. Do it. Let's see what we want to do. Now the task is just relatively simple. We have a row and actually the test input and the real input have an additional parameter that is different. So that's the line number or the row. Target row, let's call it, because quite likely I will have another variable called row. So I want to have this to be constant and to be target row. And for the test input is 10. We need to find out how many of the row 10 columns, cells, items, however you want to call them, cannot possibly be beacons, which means that they are within some of these spheres. Now we know, for example, that this thing having its beacon here means that this cannot be a thingy, this cannot be, and this cannot be, and this cannot be a beacon as well. And after that, basically everything can be. So how do we do that? Is it possible to do that directly? We need to find whether row 10 is within our circle. How do we do that? So this will be an array of all the indexes that we have covered. It will be an array. I think it's better to have it as a set of number. So this will be an array of indexes of row 10 that are already covered by some beacon. Okay, and now for each beacon, for each sensor, what we need to do? We need to find out the radius. The radius is that. According to Manhattan distance, that is the radius. How far the X is from the same beacon and how far the Y is from the beacon. Manhattan distance. Tuck, tuck. So we are just having that. And now, let's see whether row 10 is anywhere in the radius. Whether we are able to get to row 10. So if Y of this Let's see if we're getting this correctly. Console log the sensor. Actually, let's do it like this. Yeah. You, Copilot, sensor as a 218 has radius. Yeah, so this is 4 different, and this is, no, this is 5 different, and this is 3 different, so that's an 8. Which sensor did we? Sensor 87. Sensor 87, according to me, it will have a radius of 6, 3, 9. We think it has a radius of 9. And its radius is 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that is correct. So now we need to see whether row 10 is within our radius. Basically, if we add to this if the y coordinate of this, the radius, if that is within 10. So basically this means that this sensor has reached to sensor dot location dot y plus radius to sensor location y minus. Is that so? So we said 9, and it literally has 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8, 7 goes up to -2, and 7 and 9, 16. Yeah. So if 10 is somewhere within this range, if know that plus radius is less than the target row, that means that we are above it. We are way above it, and our radius does not reach the target. Or, no. It's not less than or equal, it's strictly less than. And then it's strictly more than. Are those the... So this is our maximum reach downward. If our maximum reach downward doesn't take us to the target row, that means that we're not hitting. If our maximum reach upward is still bigger than the target row, that means we are not reaching it. Yeah, that's what we want to do. Otherwise, we have not here. Let's see if we can basically ignore some some of the sensors. So sensor as 218 is not covering row 10. Sensor at 218, which is the sensor at 218. Yeah, it's this one. And it has a beacon at -2. It has this beacon. So we set, actually we already counted that. 218 has a radius of 7, 18, and 7 doesn't get to row 10. So doesn't get the row 10, doesn't get the row 10. Actually, let's see this. Okay, let's assume that is correct. Let's see how many of these are actually covering. Because for the first part, we don't really care about those that are not covering the row. Sensor at 1214 with radius 4. Yeah, 14 minus 4, that's covering one item. 8, 7. Yeah, maybe this would have been a better idea. Radius 4 covering round 10, 7 and 9 covering round 10, 0 and 10 covering, 11 and 3 minus 3 covering, 14 minus 8 covering, 7 plus 5 covering. Okay, so now we have those that are covering it. And now I would want to see what piece of it they are covering. So they are covering directly below. So one thing we know that they are covering the thing with coordinates sensor dot, yeah, dot location dot x. That's the same vertical. Yeah, so let's take this one. So they are definitely covering this one. That one, the x of that one is the same as the x of the sensor, and the y is same as the target row. So they're covering this. And this is how far to our thingy. So that means this is the reach. Not the reach, but the, yeah, let's call it row distance. That's from our row, which is row y, to the target row. And of course, we're going to need to take the absolute value of that because it can be either above us or below us. So we have our up to our radius to move. So we moved our distance to the row. We are in the 7th row and we need to take care of the 10th. We need to move 3 down in order to get to the place where we are, to the row that we need. And after that, we have how many rows that moves that we can move either to the left and to the right. Well, we have radius minus the distance of the row. That's how many we can go to the left or to the right. So basically, we can go to plus this plus this value to minus this value. So that means that we are covering from, we're going to find a better name. So we are covering from something that has, and we said that our coordinates would be sensor.location x, comma, target row. So that is where our 0 is. So we just went down. So we need to go left and we need to go right. And we're going left, we're subtracting, and when we're going right, we are adding. This means that we need to mark all of this as covered. And this will be 2xxxx plus 1. Okay, I think I got it. So this is the reach actually. Yeah, so we can say not I, but index from negative reach to positive reach. And this needs to be like this because we need to cover the positive sketch as well. Add the index to the coverts, because that's what we are covering. What we are done, log the coverts. Now I want to see the coverts themselves. What does it look like? So we have 12. This is not regular by any stretch of the imagination, but we can see that first because we had someone that covered just one, then we had something that covered quite a few more, except 12, we already have that. Then we have something that covered up to here, and then we got one that basically covered 15. Yeah, and no idea if this makes sense. This looks simple, but if the reach is something like 20,000, that means that we will loop 40,000 times to this. And sets are very fast and very cool, unless they get too big. On the other hand, sets, even these kind of sets, are much, much faster than simple arrays. So we have 27. Was that the number we were looking for? No, we have 26 positions when a beacon cannot be present. Is that so? I think somebody is fudging. Oh, yeah, we forgot the things. And this is what I was saying, that the tests for Advent of Code are kind of tweaked, because we could have taken line 11 and it would have worked for the example could have used line 11 and we would have gotten the correct result, but no, we are using line 10 because that one has a beacon. Yep, we have 27 characters, but only 26 of them are. So that means that once we have the coverts, we can do a simple for loop. And I will actually do that separately. This is quite inefficient, and that's why I'm doing it separately, because I think I might have uh, some optimization later if I need it. So this means, because note that we didn't use the sensor.beacon anywhere, except here to find the values. So if the sensor.beacon .y is equal to the target row, and it's inside the coverts. So first of all, we decided which are all the covered indexes of the target. And now we need, after we've done that, we say, well, if there is already a beacon there, remove it. And as I said, the beacons aren't unique. We can have multiple sensors that are having that. So this might be a bit of an idle work, but we don't have very few. We have very few sensors, so who cares? This will actually work fast. And if the covers, so if the Y is the target row, or the beacon's Y is the target row, and that value is somewhere covered, no, we don't need this because this cannot happen. set of parentheses. Yep. So if the censor's Y is on the target row and the X is considered covered, we are considering X not covered because it already has a beacon. Because the question is where a beacon cannot be present. And to be honest here, we know that a beacon can be present because a beacon is present over there. Let's see if we have our solution now. Yeah, of course we have one beacon and we're gonna kick it out. Now let's see what happens for the big input. This is gonna be fun and we could end up looking at the screen for an extended period of time. The target row is not 10, the target row is 2 million or something like that. Now we got our answer in about 4 seconds. I can only hope that this is the correct one, because to be honest, I have no idea, but yes, that's the correct answer. And on to part 2, which I'm seeing for the first time. It's coming from a beacon nearby. This beacon is not detected by any sensor, but the same must have an X and Y coordinates that are no lower than 0 and not larger than 4 million. It's 4 million. You need to determine its tuning frequency. Aha. Okay. Now we have a space off in the example. We have a space of 20 times 20, actually 21 times 21, 440 positions that are not covered, that yeah, if we do this map, we will see that most of these are somehow covered. And we need to find the one that is not covered in this 21 by 21 grid and return it. That's it. But there is a bit of a problem because the other task has a 4,000,001 by 4,000,001 array, which is something like million, billion, trillion. 16 trillion positions that we will need to take care of. So, okay, let's solve the small. And then we're going to think about solving the big one. So, we're going to do something similar, only we don't have a, let's put the target row 10, we have 26, and, well, let's copy this over. Something like that. We're going to have, instead of a target row, we're going to have grid size. And the grid size in our case is 20. Not want to have covers. Well, let's be silly Actually, we can this. Yeah, we have a full array of not grid size, but we're gonna need grid size plus one because 20 is a valid coordinate, is it? No larger than 20. Okay, this will not be viable because a million bytes, a million integer array will be something like 8 megabytes. A billion will have 1 gigabytes, and I definitely don't have a few terabytes of memory to have a grid size 4 million times 4 million in memory. So we're gonna need to do better. Anyway, solving the small one might give us an inkling how do we solve the large one. So we are running the input, we need to find the radius, yeah, that is the radius. We don't have a target row, so we're not gonna eliminate anything. And we basically need to draw a circle and flip out everything that's in the circle. So we're gonna run it, yeah, something like this. If we all go off the grid, we don't really care. So if our circle goes off the grid, 0-20 grid, we don't care. We have a row distance. Yeah, this is how distant we are to that. And that means that our reach with one more the radius minus the row distance. And we are running the exact same thing, only we're not adding to the cover. We are setting the map of yx. And let's try that. And let's call print matrix of our map. And we're gonna do a, not like that, but we're gonna do if the value is 0, put a dot. Put a dot, otherwise put a dash. Yeah, let's see if this does something interesting. Yay! You can see how this works magically. The only thing that is not covered is that. So we can just say yeah, let's do a stupid for loop for nope. Map.length, that's the row. It's not gonna be index, so this is the row index, this is the column index. If row of that is equal to 0, actually I'm gonna set this to -1. We just need to write some relatively simple code. X equals syndex, Y equals redex. And let's just log them, X and Y. Let's see if that works. 0, 20. No, you're lying. Not bigger than 0. Equal to 0. 14, 11. And the ones that we were looking for is 14, 11. So it's easy. Then we multiply this by 4 million and then add 11. So 14 times 4 million is 56 million and 11. That part is easy. We just need to return X times 4 million plus Y. Yay! That's the one we needed. But what happens if I say that the grid size is 4 underscore 0? Yeah, that much. Yeah, yeah, this happens. We got up to a certain amount of memory and we got this error. Heap limit allocation failed, JavaScript heap ran out of memory. So we don't have enough memory to have everything running. So we will need to think on this a bit more because I don't see any other way how to do this except seeing if we can do it in another way, but that would be also be slow. Let's say we're not doing any of this. We're just running a loop, a simple for loop that goes up to 4. Actually, yeah, let's have this. And that goes up to grid size. Yeah, this is the row index, this is the column index. And let's say we just increase the result. Yeah, notifies every, yeah, let's not be too optimistic. Notify us once you reach 1,000 items. Let's see how fast this will go on this machine. We don't have a return statement. So it just needs to count to 4 million, 4 million 1,000 times. And it did. So you can imagine that it will take quite a while to go through each, or if we do it the other way around. This means to basically go through the all 16 trillion grid, and for each point says, are you covered? Yes, I am. Okay, next one. Are you covered? Yes, I am. Are you covered? Yes, I am. Are you covered? Yes, I am. But we are gonna need to do something that will somehow check each point. Only we don't need to check them immediately. Yeah, of course I'm gonna kill this because we're not gonna wait to get to 4 million because that's really not what we want to do. So we don't need the map. We definitely don't want the map. So what would happen if I had a single set now? An array that is 4,000,001 in size, but inside each array I have something that, because each time we are doing something, we are marking a chunk of data is covered. And note that this time we don't really care about whether there's a sensor there or whether there's a beacon there. We just care whether it's covered or not by a sensor connected to a beacon, but we don't really care whether a beacon is there or not. So we can just map all of this at once. So we can have chunks. And how we will have those chunks? Well, let's just put in a type. We're gonna call a chunk that has a start and an end. The start and end will be between 0 and 4 billion. So this will give us a array of arrays, and it's gonna be an array of chunks. So yeah, we have the map over there. So we are gonna run through all of the rows, but for each row, yeah, this will help us. For each row, we are calculating the reach. And now instead of looping through the X, we can just say that's a chunk and add the chunk to the map. This is not gonna work. But let's see if this might give us some data. Yeah, this is the small one. I want the big one. How fast will it will take us to finish all the samples? Not so slow at all. So it's about 7 seconds. And let's see what we have. Map of 0. Now I want to see the map of 0 and map of 30. We can go up to 4 million. Yeah, I still think that 10-ish seconds is too slow. Oh, we can, yes, let's see what we have here, for example. Let's sort this. So this is the one that starts first, and then we have this, and then we have this, and then we have this, and then we have this. So we can see that this starts under a 0, so we can have it like this. This goes after 4 million, so we can say that this is 4 million. And this goes, we can say that this goes up to 13, which means that, yeah, since that one is bigger, so we can just merge these two, and yeah, of course, we can say this is here, so we can merge these two, and we can say this is here, so we can merge these two, and you get the point, and this means that our chunk is from the beginning to the end. Let's fix that a bit. So our chunk, and we can see that we have very few chunks on each of the lines. What is the maximum number of chunks? That would be an interesting thing to say. Maybe we can do a histogram of the number of chunks, but let's not get carried away. But anyway, I can say this is the bigger number between 0 and that one. So if we are going over under 0, we don't go over under 0. And this is the minimum number of grid size and that. Let's see this running. We will have better number, I think, better numbers, at least 0 and 4 million wise. Yeah, we have 0 here, we have a 4 million here. So now we need to add some kind of a method that will convert this, unchunk this, so to say. And I do want to see the maximum number of chunks. So we can do map dot, it's not a map. Let's call this a chunk map or chunks. Now it is a chunk map since it is actually a map of, and we can map this for each chunks. Give me the chunks dot length, and that give me the maximum. So this is the maximum number of chunks that a thing will have. This means that that line is covered by that many beacons, sensors. Waiting for a few seconds. The maximum number of chunks that we have is 13. So basically no line from 0 to 4 million is covered by more than 13 chunks. Which means, yeah, we don't need to do any pre-processing, but what we can do for each of these, we can process them. There are 4 million of them, but what can you do? We don't need this. First, we can do chunks dot sort. Yeah, sort them by the first. Once they are sorted, is less than chunks dot length. I'm using a while, not a for, because I will want to play around with the index. No. Now we have to get the first chunk and the second. Yeah, so if we have two chunks, chunk 0 and chunk 1, we want this to execute just once for chunk 0, yeah. So we have the first and the second. And let's see, is the end of the first bigger or equal than the second start? Yeah, so if the first ends after the second begins, that means that we can merge them. They are the same chunk. They are overlapping, which means that we can set the end of the first to the bigger one out of the end of the second, because we can have a case like this, don't forget. Then we can have this, then this goes to here. So the second chunk is definitely within the first chunk. So in this case, we will just remove this, and in this case, we will just say, well, you go here and you go out. So we will kind of do that. Yeah, and this will work. And so we have our chunks, and then we are staying on the same index because we get to repeat this with them. Okay? Otherwise, we found the winner. Yeah, this should happen only once, because if this is not set, that means then is a gap, and we are guaranteed that there will be only one gap of 1. Let's see if this is doing something for us. We got to the running, found the winner. Yeah, you can see that we have, actually we have no idea why this is, but in 80 seconds we managed to find the winner, because you can see that, and this is an example of what I was speaking about, because this one is entirely within this one, and this one is entirely again within this one. So we were gonna end up with two chunks, and that means that on the x of these we will have a gap. Now let's do this a bit better, because this is the column, this is the x index, and we're gonna need to transfer this into a for loop regular. So this is gonna be const chunks equals chunk map of y-index, where y-index is from 0 to, yeah, this. And now we don't need to do this. We can just return x index times 4 million plus y. Sounds about right. Let's go to the smaller input and let's put 20 as this. And see whether something happens. Result part 2 is 11. No, shouldn't be. Do we have a single winner or multiple winners? Um, yeah, that is correct. Found a gap between 13 and 15 on row 11. Oh, the y-index is in the index of the chunk. The x-index is the index of the chunk, and we are always on the first chunk, so this is always 0. So this is not this. This is actually the one that is after the end of the first, because the gap is between 13 and 15, so the gap is 14. Yay! Let's see whether this number is mentioned. Yes, exactly this number is mentioned. I'm gonna leave this in. We're gonna change, okay, leave this in. We're gonna change this to 4 million again. We're gonna put in the large input, and we're gonna run our slow and inefficient solution of this. One thing I like about problems like this is that once you establish a baseline, you get to build on that. So if I get the correct answer, I will always know against what to check. So it doesn't matter for me if my first run that actually solves the problem runs for 2 seconds, 3 seconds, or 15 minutes. The only difference that if it lasts for 15 minutes, I'm gonna pause the video while it generates the results. And I will have some console logs so that we can have some kind of feedback that it's actually executing. Otherwise, looking at a blinking cursor is one of the most boring things one can do. That said, right now we have some seconds staring into a blinking cursor until it gives us the data. Hopefully. Yay! We got the difference, and hoping that this is an actual result. It is a big old number, and it's the right answer. We're gonna return to a random character. We're gonna see everything that's going on, and now I will run all the tasks and see which percentage of the runtime is consumed with this one. And we have the results. So the runtime, the next biggest runtime is 613 milliseconds total. And this one has a runtime of 26,000 milliseconds, EA 26 seconds. So currently, task 15 takes the lead with using up 95% of the runtime. At the moment, I have no idea how we can speed it up, but I will most likely spend some time thinking about this or looking through stuff on the internet, and maybe we come up with a better idea. But still, the better idea will need to be better from a measurably correct implementation, which might be a little bit slow. Sometimes slow is good if it's good enough. But if we have a 20-second calculation, then we will need to implement something like queuing and getting the results via email and things like that. Still, it's correct. So, bye for now. Don't forget to like and subscribe, and see you tomorrow.